So yeah, my presentation is just going to be on algorithms and data structures, in particular hash tables, and how hash tables are so cool, and why I really like them, and why I think a lot of other developers like them. So yeah, let's just get into it. So today I just want to talk about hash tables, which are hands down my favorite data structure. And not just because it sounds like it should be illegal in some states or the name of Snoop's dopest piece of furniture. Seriously though, whenever I'm having a conversation with someone who's not a developer, they give me this look like a smirk on their face. Like there's no way that's a real thing. But it is a real thing. And today we're going to talk about it. Two different ways that we can group similar pieces of data together are arrays and linked lists. Now, linked lists are very similar to arrays, but they give us a bit more flexibility when it comes to performing operations, because we don't have to shift things around when inserting or deleting elements. Later on, I'm just going to do a really quick review on linked lists. And yeah, we'll get there, I promise. So we often use arrays in order to keep track of similar pieces of data, be it variables, whether it's objects or different chunks of data. Now, arrays are simple and they're sequential in memory, meaning they store data one after another in a particular order. But what about finding things in these data structures? Let's say we want to find the emoji equivalent of happiness in our array. Out of this array of emojis, we want to find the one that most closely represents happiness. Now, with an array, we're going to have to start at the beginning and go through it one element at a time until we find the one we're looking for. Now, computers are fast, and so if I have an array of only 10 elements, well, that's not too terrible. But if I have an array of 10 million elements, I might get lucky, and the one that I'm looking for might be the first element in the array, but I also might get unlucky, and I may have to search through 10 million different elements in order to find the one I want. So it could be really fast, or it could be really slow. Sometimes this is referred to as linear time operation, or they might say it's time complexity is big O of n. All that means is the expected time it takes to complete the operation is dependent on whatever the size of the array is. So as our array gets bigger, the time that it's expected to complete the operation is going to grow linearly, or in even simpler words, the bigger the list, the longer the wait. Hash tables allow us to get around this. In fact, in a perfect world, hash tables should be able to find the object we're looking for in constant time. Ideally, it doesn't matter how many items are in the data structure, I should be able to find them in the same amount of time, and it should be really fast. Now, that's the ideal case. We'll give it a bit of a reality check as we implement it later on. So how does it work? Like what's the secret sauce? What's happening? Well, conceptually, a hash table is an array with a hashing function. So our hashing function is going to take some input and it's going to map it to a location inside of our array. And that's where our item is stored, basically mapping keys to integers that will be used as indexes in our array. What's great about this is that the key that we place into our hashing function is now associated with that index arrays. So if, let's say we put an apple emoji inside of our hashing function and it gives us an index of 2, anytime we put an apple emoji inside our hashing function, we're always going to get 2. There are a lot of different ways to implement hash tables. The one we're going to be focusing on today uses a technique called closed chaining, and we'll get to that in just a minute. But before, there are 3 things I just want everybody to keep in mind as we create a hashing function, or when you inevitably create your own hashing function. The first is consistency. We want the same input to always produce the same output. It's no good if we put in something and it gives us X one time, and then put the exact same thing in and it gives us Y the next time. Two, it's got to be fast and it's got to be simple. The hashing function needs to be quick. It can't become an algorithm in and of itself. And number three, our hashing function results should be pretty random, and we need to have them randomly distributed evenly across our array. Now, I want to spend some time on this last one, the randomness, because it may not be obvious. Let's consider the most basic function. Let's say our function takes an emoji, and no matter what emoji you put in, it always produces an index of 3. Now, you can't get any faster or simpler than that. Also, this function is super consistent. It always produces the same result of index 3. But the distribution of those indexes, well, that's not random. And that actually defeats the purpose of our hash table, because it's going to try and put every emoji in at location 3 in the hash table. And if I want to store more than one emoji, that's going to be a problem. What ends up happening is any operation I want to perform is going to happen in that linear time that we talked about earlier. The bigger the list, the longer it takes it to go. So we want different inputs to produce different outputs, or different emojis to produce different locations inside our hash table. All right, so there are many, many ways to hash a value to its index, and each has its own unique trade-offs. In our example, we're going to be sticking to what's known as modular division. Modular division is, if you think back like to elementary school, it's just remainder division. And yeah, we're going to be using modular division for handling our hashing function. Emojis are typically represented as Unicode values. This is a string, no problem. Hashing functions can take any input and convert it to an index that will fit within the bounds of our array. Now, behind the scenes, we're going to take this Unicode value and convert it to its decimal representation. Just trust me, guys, this is automagically going to happen. It's going to work. Just trust me. So once we have a number, it's very easy to perform modular division on it. Now, as a side note, one way that we can help ensure a uniform distribution of those keys when using modular division is to make sure that the array size is a prime number. In this case, it's 7. Now, I'm going to take a moment here and put a plug in for prime numbers. Primes are beautiful. They're the Beyonce equivalent of numbers, but they're also great at helping ensure uniqueness when performing multiplication and division. For hash tables, they aren't going to guarantee it, but they really help in uniformly distributing our elements, or our indexes. All right, so let's generate that index. In this case, we're going to take the value returned from our hashing function and do some modular division on it. This is going to return an index of 3, and we'll add it to our array. Cool. Now, inevitably, there are going to be times when two different values are mapped to the same index location. When this happens, it's known as a collision. Now, all hash tables have to handle collisions, and there are a few different ways to do it. The more two traditional ways to handle it is open addressing and closed chaining. For this presentation, we're only going to focus on closed chaining for handling collisions, and we'll see the implementation of this in just a second. But closed chaining uses a simple array to store the indexes and then the linked list to handle any collisions. Think of it as like an array of linked lists. That's probably the easiest way to think of it. Now, before we dive into the implementation, let's just do a really quick recap on linked lists. I promised you that would happen, so let's do it. So I want to do a really fast recap on linked lists because we'll be using them when handling our collisions. Now, an array's data had to be stored in one block, like one after another. And we need to know up front where in memory an array is going to be allocated. This makes it really expensive to resize those arrays if we have to have more data that's going to spill outside of it. With linked lists, we don't have that requirement at all. They can be located anywhere in memory, and they're just connected using pointers. So nodes can be anywhere in memory, it doesn't matter. Also, they're more flexible when it comes to adding and deleting elements because they're not stored adjacently in memory. So each of these boxes is called nodes. That's just what they're called, they're nodes. And the arrows are known as next pointers or edges, and they connect each node to the preceding node. We also need to know where the elements start. Typically, this is called the head of the list. So let's just see a really quick example of why a linked list is beneficial. Let's say I wanted to add another node inside of here, another emoji node in the middle of our list. With arrays, this would have involved copying all of the existing elements and then shifting them down shifting all the preceding elements down to make room for the new element. With a linked list, this is no problem. We just allocate memory for that node and adjust those edges or next pointers so that the order we want is preserved. The reverse just happens with deleting an element. So you just remove the element from it, update those pointers, and that's it. So in a nutshell, linked lists allow us to easily add and remove elements from any location within a list. Okay, so let's see this thing in action. So we have our array, an array of linked lists. We have our hashing function, and we are going to be using the closed chaining technique. So yeah, let's just get to it. So we're going to start dropping some emojis, just kind of rapid style, and see what happens. Grimace emoji going to index 1, not a problem. Flushed emoji going to 6, not a problem. Starstruck 3, okay, we're good with that. Upside down 3 as well, we got a problem. So here is what we call a collision, but if you remember what we talked about a little bit earlier, we have prepared for this moment by creating an array of linked lists. So it's actually not a problem, which is even better. So what we'll do is we'll add a linked list to the third index, and that upside down smiley face is fine. We are dropping in the thinker, he's going in number 2. The nerd face, we're gonna have problems. Once again, we have another collision. We add our linked list element, and we put our nerd face just right in the middle. So essentially, this is how hash tables work. They basically exploit the fact that we can look up indexes in arrays very quickly, and they allow us to be able to handle collisions by using linked lists, or in open addressing, there's another way that you do it. But yeah, so just in summary, hash tables are data structures that allows for extremely fast retrieval of data, regardless of how much data it contains. In this presentation, we implemented our hash table using closed chaining and handled collision using modular division, or closed chaining to handle collision, and we use modular division for our hashing function. Hash tables are extremely flexible data structure, and based on our needs, they can easily be adjusted. We can either have a hash table that's really big, takes up a ton of memory, we're okay with a lot of collisions, or if memory is an issue, we can alter that very easily. And they're widely used just in our industry. Database indexing is a really good one, a really good example of this. Caching, program compilation, error checking. Python uses dictionaries. There's hash maps. Really, they're baked into almost every language that's out there. These are my works cited. So it's from these books and articles and YouTube videos that I was able to kind of condense down this information. And yeah, I think there should be one more. There it is. Thanks. So I can't see anybody, but if anybody has any questions, I'd love to answer them.
What program did you use to make those awesome animations?
Oh yeah, I was really impressed with it. So just Keynote on Mac. It was the first time I've ever used Keynote before. And it took an enormous amount of time to do the animations, like huge amount of time. But I think it turned out really nice. Like it made it look cool. Or at least I hope it looked cool. If it didn't, don't tell me.
It was very prime.
That was what? Sorry?
It was very prime.
Yeah. Dude, you're a good man.
It was the Beyonce of presentations of animation.
Exactly.
Cool. Well,
any other questions for Mick?
I got a question.
Yeah.
So how does I handle a situation where, so in your example, you have only a handful of, entries. There's like 20 in there, or 15 or whatever. How do algorithms handle, like, typically when you start using a hash table, you only have a couple in there, but it might grow to like, tens of thousands. And I'm assuming it just will pick a new prime number to increase the size of the hash table. Do you know how, how they recommend, basically having a hash table grow and not having your linked lists get too large if you have too small of a thing?
So they kind of have like a built-in condition for reallocating that array size. They call it's known as the load factor.
Okay.
And basically the load factor entails the number of total elements divided by however many positions there are available in the array itself. So that's kind of the threshold for when they do reallocate elements. But as far as I know,
is that a pretty expensive operation, or?
Yeah, it's very expensive. In fact, in closed chaining, I believe the advantage of having those linked lists is linked lists you don't have to know the amount of memory up front. Mm-hmm. And so it doesn't totally matter how many items go into it. With open addressing, you do need to know the amount of numbers in there or the size. I feel like I'm rambling. In open addressing, you do need to know the size of the array ahead of time. If it goes over that, then you have to reallocate a whole new array, and it's really expensive because you have to copy all of those elements in their position, reallocate the new larger array, and then paste them all in their same position. And I do know that's based off of the load factor when they do resize it. From my readings and Java, because this is how Java does it, their load factor is set at 75%. So once that threshold of like the list is filled up to about 75%, that's when they resize.
Very cool.
Did that answer the question, or was it?
No, it totally did.
Okay, cool.
Do you have an example of when a hash table is a good data type to use and when it's a bad data type to use?
Yeah, for sure. So like with anything, there's real benefits to a hash table when used properly. So a hash table, in essence, is just an associative array or like a JSON object. JSON object is fantastic until you start getting into really, really big JSON objects. As soon as they start getting really big, it might be wise to maybe use some sort of a hash table function. I believe JavaScript has maps or like hash maps. I know Python has dictionaries which do the same thing. But the trade-off that you have to make with these data structures is there's a lot of overhead for implementing these. So if you have only 10 elements, it doesn't make sense to use, in a lot of senses, in a lot of cases, it doesn't make sense to use a really big, clunky data structure with all of its overhead, because it'll just take up way more memory than what's needed. A lot of it depends on the amount of data that you're going to be doing. The hash tables are, they're great for many things. They're ideal case, and like their worst case, there's two scenarios in big O notation. Sorry if I'm going over. Two ideal cases of big O notation, worst and best. Worst, hash maps can be pretty dang bad, but that's in like the probability is very low, but their best case scenario is always constant. So you can look up, you can delete, and you can insert always in constant time. And so that's what makes them so liddy fresh.